All right, class, we're going to get started. Small group today. Was there just an exam or something in another class? Is that it? Yeah. Oh, okay. I see some nods. Okay. Got it. So there was time. Okay. So today we're going to cover response surface analysis and a little bit about how we can find an optimum response. So in lecture 19, right, the previous lecture, we talked about basically how we can design a set of experiments and visualize the design of a set of experiments where what we want to know is the effect size, right? So we talked about how we can estimate the size of an effect of one or another factor or the interaction between factors with a experiment design that looks like, for consider factor one, factor two, it looks like we have the corners of a square defining our factor space. So today we're going to talk about experiment design and a little bit of analysis when what we care about is not necessarily the effect of factor one or factor two, but what we're looking for is to find some optimum of whatever the response is. And this is, right, finding an optimum is one of the things that engineers do, right? We're asked to find we have a process and we're asked to find the optimum yields for that process or something, or minimize the time required for something to occur, or minimize the dollars required to run something. So finding an optimum is kind of core to engineering, and this will just give you a flavor of experiment design towards that. As I mentioned, this lecture and the previous one come from a different text than the standard text for this class. So I put that chapter 13 of the relevant text, Miller and Freund's Probability and Statistics, up into files on Canvas. So I encourage you to take a look at that to accompany these lectures. So before I get started, any questions? So as a reminder, exam or quiz on Monday. Yeah, so for the quiz on Monday, I'm going to put material from lecture 15 through 18, right? So not including the lecture 19 material, but yes, including the lecture 17 material, which we did finish up on Monday. Yeah, so you have not had a homework. The previous homework considered everything through P-factor ANOVA, right? That's the one you're working on right now, or that's due today. But we did not yet have a homework on inferences about variance and standard deviation, and that will be on the quiz. So problems on that, I definitely encourage you to take a look at before the quiz next Wednesday. I'll include something about that in the announcement when I post that material. But yeah, that's a good point. Yeah, thank you. Yeah, if I reconsider where I'm going to put that, I'll also make an announcement. Yeah. Okay, other questions? Okay. All right, so we're going to start by considering the problem of finding an optimum for a process with two factors, right? So we're going to have some factor A, some factor B, and we're measuring some output, and we want to know, right, what is the optimum within this. So if we think of this as our space, where we have factor one on one axis, factor two on the other axis, and now we want to find the optimum for whatever the result is within that space. Obviously, one thing you could do is just run a number of conditions and choose the one where you see the maximum, right? You get the maximum measured response. But there are two reasons why that might not be the best approach. One is that it may be that the points that you choose, even if you choose more than just 4 points, the points that you choose may not actually lie on where the true optimum within that space is. And then the second is that your measurements, right, real measurements are noisy. And so that noise may confound your ability to actually determine where the optimum is, right? So even if you do make a lot of measurements to cover this space, right, more than these 4 measurements to cover this space, if your measurements are noisy, then you may get an incorrect idea of exactly where the optimum is through that space. So just to give you an example, in one dimension, so my lab does this all the time, we do a lot of microscopy and imaging of cancer cells to try to measure their response to therapy. So one of the things we have to do is autofocus, right? Something that your camera on your phone or something does automatically, but we have to implement this ourselves using our microscope. There we only have one factor, which is the position of our, or the position of our microscope relative to the sample, so the focal distance. And we measure a parameter. The parameter we measure is the sharpness of the image, or how in focus the image is. And when we do that, we're doing this from images that are noisy, that have some amount of noise in them. And so if we just take the position, the Z position, that gives us the absolute highest score, highest focus score that we've seen, oftentimes it's not actually the optimal focus. It's really just the one that was some combination of being pretty good focus plus maybe some noise that made it appear to be the best. And so in that application, we fit with a parabolic curve and find the optimum of that shape. So here we're going to talk about how we can do that, or how we design an experiment, and then how we analyze that data when we have a two-dimensional region, right? Two factors that we want to investigate. But again, we're going to design it to fit with a parabolic response surface. So the suggested experiment design when we want to try to find an optimum is not just the corners, right? Remember, from just looking at the corners of the space, we were able to estimate effect size. That was in the previous lecture. But if we now want to try to fit a response surface to our resulting data and figure out what kind of the shape of the response looks like where the optimum might be within this region, we need more points. One suggested experiment design for this, it's called Box-Wilson experiment design, is to take our square and we're going to add a star of conditions to that square. And this is what the resulting set of experiment designs looks like in this kind of abstract format that we saw last time in the last lecture. So this design, the corners plus the star, is, as I said, one version of Box-Wilson experiment design. And the idea is this will allow us to fit a second order response curve and find an optimum. If we just had these four corners, we don't really have enough data to even fit a second order curve. And the reason we're doing a second order curve, or think of it like a paraboloid shape in two dimensions, the reason we're fitting to a second order curve is because then there is some optimum. We can find some maxima of that shape. Whereas if we're fitting a plane to the data, that's more or less what we've been doing so far. If we fit a plane to the data, then there's no curvature, so there's no sort of optimum point that we can define. So, well, with this experiment design, we can then do that kind of fitting. So, for an example, we'll say we've been asked to optimize the production of a coating compound, and we think that temperature and some additive, or some amount of an additive, are the essential factors that affect the yield of the compound. And we suspect, maybe based on previous results, literature on this, intuition from having done this before, that the range of temperature, the relevant range of temperature, is between 100 and 180 degrees C, and the relevant range of additive is from 0, we don't add any, all the way up to 70 grams of additive per kilogram of the mix. And so we have those two factors. We run experiments at that kind of corner plus star configuration, and these are our final results. So we have these now listed by run. We have varied the concentration of additive, we've varied the temperature, and we've measured this for the yield. So one thing, actually, before we get too much further, another aspect of experiment design. So in addition to how we choose the conditions at which we run the experiments, it's also actually important, but sometimes underappreciated, that you should randomize as best as possible the order in which you run those conditions. So it may be tempting, for example, to just take the additive and do all of your experiments at 0 additive, and maybe across your different temperatures, and then do all of the experiments at the next concentration of additive, and then all of your temperatures, and then all of the concentrations, the final concentration of additive, and then all the temperatures. That's a tempting experiment design, but that introduces the possibility of bias into your results, where maybe there's something else going on that's changing as a function of time or changing as a function of run. You're doing this on a piece of equipment that's degrading over time because of the temperature, or your the other materials in your mixture are aging over time in between these runs, and so they're not as fresh by the end. And so if you have a non-randomized set of conditions in your experiments, then you may confound the effects of something else that you haven't considered with the effect of one of the things that you were actually trying to vary. So you can see in this experiment design, we don't have substantial groupings of, we're not doing all the temperatures, all one temperature at once, or all one additive at once, right? So we're randomizing that. There may be practical constraints, like maybe you're running this in a setting where it's really, really difficult to vary the temperature, to take the temperature back down once it's set at a certain set point. In that case, you'd maybe at least want to avoid running the temperatures in order if you can, right? So you wouldn't do 100, 140, 180. You'd maybe try to do 100, 180, 140 at least. But as much as possible, you want to make sure you randomize your experimental conditions in your experiment design, in addition to considering how you choose the points. So for this problem, the rest of this problem statement, so your economic analysis shows that the yield should be at least 95% in order for the process to be acceptable. And so what we want to do is estimate the response surface and find the optimum region within these two parameters, additive and temperature, within which we would operate. So we have that data loaded here in this CSV file. This is what the start of that looks like. Same results we have up above. And what we're going to be fitting to is a second order response surface that looks like this. So we have some set of parameters, beta, and we're going to fit to some offset, beta not, plus beta 1 times x1, beta 2 times x2, right? So those are the linear contributions of each of the individual parameters. We have these quadratic contributions of each parameter, and then the interaction between the two parameters, right? And so that's going to define our parabolic surface across these two factors. So in order to do this practically, we're going to add columns into the data frame in order to include those nonlinear terms, so we can do the fitting, or to help us with the fitting. I mean, there are other ways of doing this with other kinds of packages, but this is a way to do this with OLS in a data frame, right? So our data already includes a column for x1, a column for x2. So we're going to stick in a column for x1 squared. That's here. We'll call it x1, x1. A column for x2 squared. That's here. And then a column for x1, x2. So now when we have that, we then define our model. Again, we're doing this in OLS. Note that we're not using the C, the categorical casting that we did when we wanted to do ANOVA, right? Because these are continuous valued results. And what we want to do here is a fit, surface fit to these continuous valued results. So we're not telling the OLS method to treat these as categorical data. And now, so we're going to fit this, and we'll see our results. So we see a very high R squared value, indicating that we have very good confidence in the results. And if we scroll down, we see our the coefficients on each one of our results, right? So now those are our betas that we can read out here in this second column of this table. So from this, right, so now we're reading out the parameters of the model, which again give us those coefficients, right? So you see these are the same as what was listed here. We can then access a specific parameter by pulling out a single value from model.params. And now we're going to visualize these using contour plots, right? So we can actually visualize what the response surface looks like so it'll be a 3D surface, right? So it's a surface over two different factors. And so this is what that looks like. So if we take, so we're going to take our data, we're taking our results, our parameters that we got from curve fitting, and we're now going to, so we've created this mesh grid, which is basically just it takes a list of, in this case, X and Y, right, which are defined over the range of parameters that we're interrogating. So this tells us we're making a list of X values from a list of 100 X values from 0 to 70. That's for the additive, and we're making another list of 100 values from 100 to 180. That's for the temperature. What mesh grid does is then, so that would define, like, I don't know, vectors that go in one direction, in one dimension. What mesh grid does is turn that into a big mesh of all values. So we have this big array corresponding to X and Y. And then we're going to use those to actually construct what the response surface looks like by taking in each one of the individual parameters from our fit and multiplying it by the proper values of X and Y. So when we do that, then we're going to use this contour function to plot it. And this is what our end result looks like. So, and here we've superimposed the measurement points in red on top of the response surface in this kind of yellow to dark blue, or dark blue to yellow color map. So from this, we can see that it looks like there is some optimum region right down here, right? And this is why we were fitting to a parabolic response surface, because it's possible for it to have a shape where we can potentially see an optimum. And so now the question is, what is that optimum? What is the yield at that optimum, right? Does it exceed our 95% level? And basically, where should we either operate, or maybe in what region should we perform some follow-up experiments to get a better idea of this response surface and really try to nail down our operating conditions. So because we have fit this just to a parabolic response surface, we can then find that optimum analytically, right, just using calculus. So we're going to set the derivatives of our surface with respect to x1 and our surface with respect to x2 equal to 0, and try to find that point. In this case, so this is what that looks like in equation form. Here, now we've put this into matrix form, so we can solve it just a little bit more easily. So now we define what those parameters are out of that model.parameters structure. And now this code block here is implementing a matrix solution to the matrix form of those equations, so that we can actually find the x1 and x2 values, the position of the maximum additive and temperature. And then from that, we can predict what the maximum yield would be. So from this, we find that the optimum additive is 31 grams per kilogram. Optimum temperature is about 115 degrees C. And our predicted maximum yield is about 92%. So from this, we conclude, we know roughly where the operating condition should be. So this is now a response surface that's again plotted using that contour plot. An estimated response surface for yield. We've now put in that optimum potential operating point here, labeled in green. So this tells us, roughly where we might want to run our process is somewhere around here. Note that this is really just an approximation, right? So if it were really critical that you had the highest yield possible, you would probably want to rerun a set of experiments, really narrowing in on this point in order to determine what your optimum was. But at the very least, it tells you where to look. And it also tells you that since the estimated maximum yield from this is only 92%, then it's likely that your maximum yield of 95% is not possible, but you might want to run more experiments in order to figure that out. So, we could go further than this into placing confidence intervals on that from the curve fit, but that's where we're going to leave it for this analysis of response surface in this class. Any questions on that, on 2D response surface? Okay, yeah. Yeah, so to what level of detail should you know this for the final quiz? So today is going to be more, you'll see today is more conceptual, right? So it's more about concepts and experiment design, how we design experiments. A little bit here that calls back to what we learned about curve fitting, right? And so, more questions about curve fitting and how to understand the output of the curve fitting routines, that kind of thing would certainly be fair game. But then I would expect more things about the concepts. And we'll see when we start talking about response surfaces for greater than 2 factors, we're going to actually delve into a much more conceptual discussion than we ordinarily had been. Yeah. So does that answer your question? Kind of enough. Yeah. I can't tell you exactly what's going to be there, but yeah. Mm-hmm. Yeah, so it's about how we can, and really one of the key concepts here is about how we design the experiment in order to, or set up the experiment in order to estimate a maximal response. Yeah. Okay, so I want to talk a little bit about response surfaces for greater than 2 factors. So it's often the case that you have not just 2 things that we care about. In this case, it was or 2 things that we think are important, right? So it was temperature and additive concentration, right? But there might be some other factor that we think is really important. Maybe it's the time, right? Overall time, if it's a batch process, the overall time we run that process or something. So it's often the case that we have more than 2 factors. In fact, when you really get down to it and you start trying to design experiments, it can be very difficult to limit yourself to only 2 factors, right? It's often the case that there are many things that may influence your result, and you have to narrow your search down, sometimes pretty significant. But so if we have, so we're going to consider 3 factors as an example, but the same kind of concepts extend to higher dimensions as well. And we're going to start by looking at 2 common approaches that are, maybe the most naive or initial approaches that you might be tempted to take in designing a set of experiments, and what the drawbacks to those methods are, and then how we can overcome some of those drawbacks with better experiment design, better exploration of our design space. So those 2 common approaches would be full factorial design and one at a time design. So full factorial design would be, let's consider we have 3 factors, A, B, and C, right, plotted along these 3 axes. And let's say we're going to divide each one of those factors, or the space for each one of those factors, into 3 potential levels. Then full factorial design would involve testing every single one of those levels, right? Every single one of those combinations of levels. So in this case, that would be 9 times 9 plus 9 plus 9, or 27 total different combinations of all of the factors. So exhaustively testing all levels of the given factors. It would be full factorial design. And now this approach, if possible, gives you a great idea of what the overall response surface would look like within that 3D space. But the downside is that you have to run 27 different experiments, and that may be costly, or may not even be possible, depending on exactly what it is you're trying to investigate. So if what you're trying to do is to find the optimum condition within this space, we can definitely do better than that. So it can lead to a well-fit response surface. So we can definitely fit a surface here, but it's often expensive. And so if we had just a same number of levels per factor and some number of replicates, right? So we haven't even talked about replicates of the experiment. Then this scales pretty badly. So we end up with a lot of experiments, and it can be quite expensive. Right? If possible, it's great, but it can be quite expensive. So one way to overcome this, or maybe sometimes even the first thing that you might try, would be one factor at a time type design, where instead of varying the factors together, you just say, maybe starting from some center point, just vary each one factor at a time away from that center point. This may be attractive because you think, well, I'm controlling for everything but each individual effect, right? Each individual factor. And so, that might be attractive as an experiment design. But the major drawbacks here are that you're getting no information about interactions between the factors, right? So remember, one of the themes of the different types of analysis that we've been doing, right, for like multi-factor ANOVA or the effect size, or now the response surfaces, one feature of all these different types of analysis has been to capture the interactions between factors. But if you only vary one factor at a time, then you really get no sense of what those interactions might be. So this kind of design, and you can see graphically, you're leaving out like all this space in the corners is just completely not accessed by this type of experiment design. So we can't really meaningfully say anything about what's going on in those corner regions with this kind of design. So just to call back to, for two factors, so we said that the suggested experiment design for fitting a response surface, that Box-Wilson design, was a box plus a star. If I scroll up to it, let's scroll back. It was actually a full factorial design, right? So here it is graphically. So when we were fitting a response surface in terms of two factors, what we ended up with was actually just a full factorial design at 3 levels. But when we're going to higher dimensions, we don't have to do a full factorial design, and if we are trying to fit a response surface. So the analogous kind of star plus box, in this case, it's like a 3D star plus cube design. This is the Box-Wilson design. So we see in this case, we're hitting all the corners of the cube. And also we have this kind of star shape that's in the middle, right? So it's kind of a cube plus star. This kind of experiment design also allows to study interactions among factors, because we're hitting the corners, right? We're in the midpoint of this face, so we can see things about interactions among factors. With this kind of design, we can also estimate a response surface. So we could fit a paraboloid, a 3D or 4D paraboloid, and get a response surface to this. But if you count this up, you'll see this is only 15 experimental conditions compared to 27 for full factorial. Right, so we're doing a lot better. We're sampling the space more efficiently than we are with full factorial design. So this is one option. It's called Box-Wilson. The most famous, though, experiment design is the Box-Benken experiment design. And so this is one that you'll often see if you ever encounter anything on design of experiments in the future or in your career. If you're setting up a set of experiments to try to optimize some kind of process, you may encounter this. And Box-Benken experiment design in 3 dimensions, there are different variants of it, but the most typical variant of Box-Benken experiment design in 3 dimensions looks something like this, where we have an experimental condition at the center of our factor space. And we actually don't test the corners at all. Right? We're not testing the corners at all, but we're testing like the midpoints on the faces between all of those corners. And so with this kind of design, we end up with a response that does pretty well, even when we do pretty well even when the response is nonlinear. So if we have some optimum lurking in there, then that implies that there's some kind of nonlinearity, and we're going to tend to do pretty well with the Box-Benken design. And in this case, it requires even fewer experiments, only 13, than the Box-Wilson cube plus star design. So it's even more efficient. And that's why Box-Benken design is often used. And this is something, I guess, in getting some feedback from former graduates. I know at least one former graduate came back. This is something we used to cover in senior project class when we talk about experiment design in senior project class. It may still actually be covered in that class. And at least one former graduate of the program came back and said that they had gotten a job in part because they were able to talk about what box banking experiment design was, because it was being used at the company where they were interviewing with. And I can tell you I'm working with a senior project group right now that's doing an industry-sponsored project. And one of the things that their mentor at the company wanted to do was to lay out an experiment design in this way. So this is something that's relevant, although we're just talking about conceptually here. What this is something that's definitely directly relevant to work, potential job that you might, and something that you might see on the job later on. So when I show this, do you know what it means? Like, what does this condition mean? So let's say I have 3 factors. One is, this is temperature. This is, concentration of my additive, just like I had previously. And the third one here is time. All right, let's say I ask you, like, could someone tell me what this corresponds to? So remember, this is the temperature axis. And let's say this bottom corner here is the lowest of all 3 parameters. So what does this correspond to in terms of those different parameters? Yeah, I want to take a shot.
So that'd be the first concentration
at the second of the 3 temperatures. That's correct. Yep. So this is presented in this abstract way, and we've gone through all of this in this abstract way, I guess, building on what we did in the previous lecture. But yeah, one thing to make sure you understand here is how we can map this back to the actual conditions that we're actually trying to test. Does anyone have a question on that? Right, so that center point, right? So if we have 3 levels of each factor, that center point would be the second level of each factor, right? Because it's 1, 2, 3. The center point is the second level, would be the middle point of each. And yeah, the main feature of this box banking is we're not doing those corners. Okay, yes. Mm-hmm. Yeah, so if we had more than 3 levels for each factor, how would that affect things? Yeah, so that would be a question of, like, if you needed higher resolution within the space, how would you lay it out? And as I said, this is one example of box banking. So there are other box banking type layouts that could account for more levels of the factors or more factors, right? So if we want to extend this to higher dimensions, or even like different considerations about what it is that you're trying to do with your experiment design. So for that, I would say consult literature on design of experiments, and it would be laid out more or less like what is the, in some sense, this is an answer to the question of like, what is the statistically optimum set of conditions at which I should run my experiment to minimize the number of experiments that I have to run, right? So minimize cost, but maximize the information I get about response within this space, right? And that question, so if you now increase the number of factors, increase the number of levels, or you have questions about where to run replicates, so we haven't talked about where to run replicates. Those questions are actually all answered in some sense, right? In this kind of design of experiments literature. It's a whole field unto itself, more or less. Yeah, so we're just scratching the surface. Okay, other questions? Okay. So I just want to talk briefly about optimization. So if we have a nonlinear, if we have a non-parabolic surface that we want to, or non-polynomial surface that we want to fit to, which is sometimes the case when we're searching for an optimum. So, and we're again just going to barely scratch the surface of this problem of optimization, which is, I believe, something you're going to talk about more in numerical methods. But it does bear on our discussion right now. So in our previous examples, we used calculus to find the maximum yield. And in general, if we're fitting a parabolic surface, even if it's in 3 dimensions, we can also still use calculus to find the maximum right within that space. But it's often the case that we don't just have a polynomial surface. And so it may be a little bit harder to just directly use calculus to do the solution. And so there are many ways of finding the optimum. So here's one example. Actually, it's just one example of how this can be done. So in this case, this is, we have some surface that we want to minimize. So here, x1 times x4 times the sum of x1 through x3 plus x3, right? So we have this very nonlinear looking function where it involves, the combination of some of these variables and not others. And in this case, it's subject to constraints. So, it may be the case, right? This is another case where that polynomial, where the calculus approach isn't going to work. So it may be the case that even you have a polynomial surface that you're trying to fit to, but you may have some constraint on, the maximum, the combination of temperature and there may be some combination of temperature and concentration of additive that is just not viable because the additive is going to break down or something. There may be some combination of temperature and time that's not possible because of some other constraint on the equipment that you're using. So there may be, it's often the case that there may be some constraints on the responses that you can seek. But even if that's the case, we can still handle this using optimization techniques. And so in this case, in this example, we're going to try to minimize this. Think of it as like our cost function. So we're trying to minimize whatever that cost is, subject to these constraints. All right, so this defines some limits that we cannot exceed. And we're given an initial guess for our x1 through x4 based on previous data, intuition, or maybe just a good guess to start with. So SciPy has, in this case, we're going to be using the SciPy library and the minimize function from SciPy library. We have to define an objective or cost function, and this is the thing that we're trying to minimize. And so this resolves to what was written up above in the equation above. And then we define our constraints as well. And then we're going to input our initial guesses, hovering over it and getting the help tips. And then we're going to use that minimize function in order to actually find the minima. So when we do this, in this form, we're given, in this case, one of our outputs was what is the, at that initial point, what was the cost function or the function that we're trying to actually optimize? And we saw its value was 16. Our final value was 17 with this solution, meaning that we had found something which is larger than our initial guess. So this was string.objective, meaning we found something that is greater than what we put in. Let me see. Now if I run all, and I don't know why it is greater than the answer that we put in, other than that our minimize function failed. And we did not, in fact, find a minimum to this. My guess would be that this function does not satisfy our constraints. It satisfies this constraint. Yeah, so what's happened here is that our minimum does not satisfy our second constraint. So sorry, our initial value rather did not satisfy our second constraint. So what the function's done is, so we've taken this initial guess, and at that initial guess, our objective function, right, our cost function was 16. But if we look, that initial guess is going to be 1 plus 25 plus 25 plus 1, so it's going to be 52. So doesn't meet our constraint. When we minimize, we then found a new location which does meet our constraints, and our minimum was now 17. So the minimum that we can actually achieve was 17. But in any case, this is really just meant as an introduction to this concept of optimization, and we can optimize much more complex functions than we can analyze using calculus. Any questions on this before we end it for here? Okay, so as a reminder, we have our next quiz on Monday. And then next week on Wednesday, I'll be doing a Zoom office hours. So I'll be hanging out on Zoom in the office hours room to answer any questions that you have. Okay. All right. Thank you all.